All right, now for the second lecture on our second section of Chapter 9, calculating centroids. And many of the centroids, for manufactured items in particular, are going to be known. And the way we can do it is we can take combinations of things for which we know the centroid and combine them. And that's typically what's going to happen. There's tables and tables and tables full of different shapes and what their centroids are, and you can use things like Inventor, SolidWorks to calculate those. So here's an example. Suppose I need the centroid of this compressor and its assembly, and I know the centroids of the different pieces. Well, I can use not have to do an integral, but I can use those and do them as discrete things and sum up to find the centroids that way. And that's what we want to learn. And that's back to that slide we had earlier. If you had a discrete set of objects, then you can simply go, depending on which you want, center of mass, centroid, or center of gravity, which basically are all the same, then you can go area times x for each one of them, divide by the total area, or mass times x, depending on what you're looking for. So that's the way we abbreviate those. Instead of integrating x times dA, x of the element times dA, and divided by the area, we'll do it by summing them. And then you have an x, y, or z coordinate of the centroid. So here's a couple of good examples. Here's a beam. Here's maybe a cutter. It looks like a blade from a box cutter. And so the trick is figuring out what shapes to make it out of, and then being careful. One thing to note is that you can do a hole by taking a solid shape and then making the hole a negative area and then using those same formulas. So here's a table. A table that's out of the book. I forget exactly where in your book it is. It used to be on the back fly. Not sure. I think in 13 it's still on the back fly. But you can see you've got a variety of different shapes that you know the centroids to. We talked about the area, third of the base measured from the height. We got the centroid of a quarter circle, half circle, full circles in the middle, obviously. We have parabolas, various shapes. There's a circular sector, and there's the formula. And we'll use these formulas. That's where we'll go get our formulas from in order to do the problems we're fixing to do here in a minute. You can do it for a plate, for example. So suppose we have this plate, and we're going to break it up into a variety of these areas and calculate the centroids of each one of these because they're just triangles or rectangles, and then add those up. Great way. My example when I work it out, I'll do with Excel. Excel works really great for doing this. So the step for analysis, remember holes are negatives, but you break it up, decide how you're going to sum up that object, whether it be an area or a volume, and then you make a column of x times your centroids of the piece times A, and then you get your total area. So here's one. Here's that blade we were talking about. How do we want to divide that up? Well, clearly you got a hole. So I think we could probably do something like a semicircle for the top, and then a hole, a box, and then a triangle. Now the key to it, the thing that you have to be really careful of, is you have to pick a coordinate system because you're calculating the x and y coordinates of the centroid. So they have to be real, and you have to keep the same coordinate system for each piece. So like so many problems we've done, you have to pick where your origin is and stick with it. So, and this is a nice technique to draw it up like he's done here. This is going to be equal to the rectangle for the center, the lower triangle, the upper semicircle, and then the hole. And so then, like I said, you can see this going right into Excel. So you got each piece, you calculate the area of each piece, making sure your circle, your hole is a negative area. And then you'll get your total area. You find the coordinate of the x and y of that piece. So the x and y of a rectangle's in the middle. So he figures where that is. Then you make the product of x times a and y times a. And then here for the triangle, third of the base measured from the height. So if I'm measuring down and treat this as the base, that's a third of the height. So it's 60. So it's going to be a third minus 20. So we see the y coordinates minus 20. You do the same thing the other way. Treat this as the base and go across. It's got a height of 120. a third of the height measured from the base, so that would be 40. So the coordinates of that are 40 and minus 20. And then our semicircle. Now you have to look that one up. Of course, the area is power squared for the circle, take half of it. And then if you look that formula up for the semicircle, you'll see it's 4r1 over 3 pi. Will be that distance, then you have to add the 80 to it. So that's how we got his y. Clearly for the r, it's just over on the radius, so 60. And then product, and then your circle, again, you got its area, it's in the middle of it, but again, it's coordinates, so you got to, where's the middle relative to the x and y axis? So it's 80 up and 60 over. And then you do your products, and then you add all of these up, and then you simply divide. Well, he's calling those as qx and qy's, and then you're going to divide that sum by the total area to get your x coordinate, and that sum by the y. That sum of the y times your area is over y, and then you have your x and y coordinate. That'll be the centroid of that particular piece. All right, I'll work one out in detail for you and post the solution and the video later on. Talk to you later.